Hello, I'm answering the question above, which is essentially um, show how show that efficiency of power delivered to a load is highest at high voltages. So what I did is I already wrote out some of this, and I have this right here, which is the sum of all the powers out divided by the sum of all the powers in is equal to the efficiency. And then in this equation, we have this setup right here. You can read the question and double check that I'm right if you feel like it. And the sum of the power output is equal to the power on the wire plus the power of the load. And the sum of the power input is really just equal to the VP, which is the potential across the battery, or the power source, times the I in the system. So what I then do is I find that, or I take the power of the wire and I take the power of the input and I minus them, and that will equal the power of the load, because the power in is coming around or being used right here. Like, this is the power input into the system. It is then used through this wire, hits this power of the load, reduced there, and then it again follows the system. So it's just this minus, or the power inputted right here, minus the wire, which is equal to this power load, which we do not know. So I then take, and this power load, since I know these two right here, the wire still follows Ohm's law, so the power of the load will be equal to the VP I minus, and for this one, I'm going to use the definition of power, which is the current squared times R. And since we know the resistance of the wire, or we could know the resistance of the wire, and it follows Ohm's law, we can get this equation. And then I will take the definition of, I'll take this equation right here, which is the power of the wire plus the power of the load, which is right here, and that will equal, sorry, it's right here. Power of the output is equal to this, and then the power of the input, which is VP over I, or times I. So we're basically taking this definition, setting it equal to E. So then, and since I could have now a power of the load, I can plug that in right there. So what I end up getting, take out my work right here, is that VP I minus I squared times R divided by VPI is equal to E. I then cancel these two out, and that I is also divided. So what I end up getting is 1 minus I R divided by VP, which is equal to the efficiency. Now, if you plug numbers into this, you should get that the more power you supply to the system, and if the I and the R, the current and the resistance, maintain the same values, we'll be getting closer and closer to 0, which means that as this number, if we plug in, say, this total value up here is 10 amps times ohms, and then we divide it by the, say, 10 volts, that will be equal to an efficiency of 0. So if we have 1 minus 10 divided by 100, that will be an efficiency of 0.9. And say we have 1 minus 10 to the 1000, that will be equal to 0.99 efficiency. And we can just keep going up like that, and which shows that the higher the voltage is, the more efficient the system is.